So today we're talking about kinematics of spike ball. So the perfect spike ball set would be right over the net. So ideally, I can hit it anywhere I want. So, for instance, let's just say I'll be 6 feet off from the center of the net. If I hit the spike ball perfectly, or the perfect set, I would see how fast I should hit the spike ball. That's about it.
All right, so now after that demonstration video, let's go through the kinematics of a spike ball. So here's a sketch of what I essentially demonstrated outside. So in the Y direction, we have 3 feet above the net because that's where my hand is in relationship to this net over here. And I'm standing 6 feet off from where the ball lands. And then we just estimate about a 60-degree angle of how I hit the ball out of my hand. So our goal here is to find the initial velocity and the time it takes for the ball to leave my hand and reach the net. And then here are our givens and assumptions. So for our measurements, we're given that the distance in X, it travels 6 feet, and the distance in Y will be -3 feet, and our theta is 60 degrees. And with any engineering problem, we need to assume that we have no drag, we have no acceleration in the X direction. So whatever initial velocity we're given in the X direction will be the final X direction velocity, as there's no resistance in the X direction or any acceleration to make the ball speed up or slow down in the X direction. And then we also got to treat the ball as a particle just to make things simpler and not have to deal with real life objects. And then we also have a constant acceleration due to gravity in the Y direction. And since we are in feet and we're doing feet per second squared, it is -32.2 and not the SI units of -9.81. So here's our sketch again. And then here I have established my coordinates of X and Y. And I put our origin right where I contact the ball. So anything below it would be feet would be negative feet, and anything to the right here will be positive feet for the X direction. So now let's go into our analysis. So since we know we are dealing with either no acceleration or constant acceleration in the Y direction, we can use this kinematic equation where D equals V naught T plus 1/2 AT squared. So when we set that up in the X direction, we know that X of T is equal to V naught X of T, or V naught X times T plus any displacement in the X direction. And then for what we also cancel out the acceleration in the X direction, given our assumption that there is no acceleration in the X direction. And then for Y of T, we have V naught Y times T plus 1/2 AT squared. We do have the acceleration here because we know we have gravity affecting our Y displacement, and then plus any displacement in the Y direction that we might already have. So when we go to solve this, we can plug in our givens. Let's start with the X equation where we know we are traveling at 6 feet. So we have 6 equals V naught, and then we get rid of the V naught X because we have cosine of 60 degrees to account for the X direction times T. And then solving that out, we know cosine of 60 is 0.5, 1/2. And then bringing that to the other side, we have 12 equals V naught times T. And in the Y equation, we have a -3 in the direction because we know if I have my origin from my hand, it would be dropping -3. It would be dropping 3 feet, meaning it would be a negative. And then V naught times sine of 60 degrees to account for our angle times T plus 1/2, and then our acceleration of -32.2 feet per second squared times T squared. And then solving that out, we get -3 equals V naught √3/2 for sine 60 times T minus 16.1 T squared. And those would be our two equations, and however you want to solve that out, I would just use my calculator, and then I would know that I would have to hit the ball at 13.15 feet per second, and that would be the initial velocity, and the time it would take from my hand to reach the net would be 0.912 seconds. Thank you.